Hello, everyone. I'm Ritesh Vajaria, and today we are joined with Mani Kanuja. For today, we're going to discuss how you run thousands of AWS GPU with Amazon SageMaker model training. And we'll walk you through some of the slides to get you accumulated with the topic, and then we'll straight jump into what we call the SageMaker notebooks, and we'll go through some of the exercise on how you do a distributed training on SageMaker. All right, let's get started then. So this is the agenda for us. We briefly touched upon landscape on AWS of AI/ML. We will talk about how you train the machine learning model. On SageMaker, the large-scale training, particularly we will focus on model parallelism, if you are aware of that term. If not, don't worry, we'll go through what model parallelism is and also the data parallelism. If time permits, we will also talk about how you can tune your cost with a spot training, and finally we'll conclude with the takeaways. So from a AI/ML landscape point of view on an AWS, I'm sure you have seen this slide probably a few times if you have been involved with AWS in the journey. But just to recap, primarily when we talk about AI/ML stack, we define in 3 different tiers. The bottom tier, what we see is the ML framework and infrastructure, particularly where we provide the infrastructure, the best of breed infrastructure from a compute, network, and storage point of view. And people who are expert and they want to manage fully the entire layer of their own, they would use ML framework, and then deep learning AMI is what we provide. If the user choose not to do it on their own, the middle tier, where what we call the ML services. And this is the layer where, with a service called Amazon SageMaker, where you can build, deploy, and run your entire machine learning workflow on SageMaker. And the AI services, primarily we have defined in 2 different categories. One we call the specialized, and the other is core. And when we are talking about specialized, it would be our code and DevOps and some of the other area like industrial services, where even a simple developer, you don't need to be a machine learning specialist, but as a software developer, you can make an API call and then run through your AI services. We'll briefly touch upon how would you train the machine learning model, particularly with Amazon SageMaker, as you have probably heard it many times in past, where Amazon SageMaker is a fully managed platform, and you can do not only the training part, what we are going to focus today, but you can start with your building part, then training, then deploy, and you can monitor your entire model lifecycle. And with MLOps, you can do an end-to-end automation. But today's focus is on training. So there are many ways you can train your model on Amazon SageMaker. You can start with a built-in algorithm, what we have provided. And there are many model range from supervised and unsupervised algorithm, whether it's on the NLP domain, whether it's on the computer vision domain, or you are doing a forecasting of your sales revenue or any regression models or whatnot. It grows from there, and there are techniques called a script mode, the second option you may have, where you can build your own Docker container, or you can use our own Docker container and build from that, and then train from your container and launch from your container. Quite often when you are using a script mode, you are relying on something called ECR, which is Elastic Container Registry. So your container registry would be ECR, and then you are pulling your container from ECR to train, whether you want to train using MXNet, PyTorch, TensorFlow, or any other framework. We have the deep learning AMIs created from a container images point of view for you to consume and use it. Okay, so how would you train on Amazon SageMaker? And then we will go through in detail when we go into the actual notebook section. But somebody who has not trained for a while now, it's sort of a refresher that when you issue a training job API on Amazon SageMaker, particularly here, we will give you an over full flow, right? So when you send that API request, the first step as a part of that request is you supply certain information, like your EC2 instance type. So there are like many instance type we support from a CPU, from a GPU, and whatnot. And you choose which one you want. You also identify which container image you want to download. So maybe it's a TensorFlow work you are doing or a PyTorch work you are doing, and maybe you want to pull the image from for a TensorFlow or a PyTorch. You would also need certain storage. So there is something called EBS volume. So you define what is that volume size. Maybe it's a 30 gig, 100 gig, depend on your size of your data. And eventually, once we have information, what SageMaker control plane, when it receives this information, what we do is we provision what we call an ephemeral cluster. And that ephemeral cluster is independent of your notebook. So your notebook might be running a 1 CPU, 4 GB memory. But when you launch that container with, launch that training job with the EC2 instance you define, maybe a GPU, we will spin up that GPU box. We will bring in all the data, where you specified, whether the data is residing in NS3-like storage, whether it's residing in NFS-like storage, which we call EFS, or a high-performance storage like FSX, right? So from any of those places, the data is being pulled into these instances, whether it's one or many, depends on what you define in your manifest or in your configuration properties. And once that information is out there, we start training your workloads or applying your script and applying your Docker container if that is a custom Docker container, and the training begins. And once your training job is complete, what we do at the end is during the training job, the data, the metrics, and the CPU, GPU, memory metrics, all this information are captured, and your logs are captured in Amazon CloudWatch, and your model, your artifact, gets stored into an S3. And once we commit that artifact into an S3, we terminate that GPU or the CPU instance what you provisioned, or we provisioned on your behalf, and it goes away. So you only pay for the duration of your training job is running, right? So this is just a refresher. We will go through this in detail in the practical scenario. And then this is just a snippet of what the training estimator would look like from the parameters, what is applied, like the CPU or the GPU machine, and what is your framework you want to use. This is a TensorFlow example. Cool. So this is a refresher on a training. Let's jump into why we are here today, particularly talking about the thousands of GPU, why you need that. So from last few years, at least last 4 or 5 years, customers have gone using the model. They were initially using like 100 million parameters, like GPT-2 or BERT. In this scenario, GPT-2 is 1.5 billion rather. But for BERT, it was like 340 million. And then customers have started growing further. And then now they are training models which are not in 1 billion, but in the range of hundreds of billions parameter. And in some cases, even it's going into a trillion of parameter. And so particularly in this scenario, your model size is growing. But as your model size is growing, why you want to grow your model? Because you want to have a higher accuracy. And yes, as you grow your model size, your accuracy is going to improve. And that gives customers the benefit of either doing a zero shot or a few shot learning during the inference. And that means it is reducing their latency from few minutes to maybe a few seconds on how fast they are able to make a prediction, right? So the smaller the window of your inference, better for your business, and you might be able to make more money out of it. So as the model is growing, there are some improvement in the hardware, but the model are growing faster than the pace at which the hardware is growing. Right. So in this scenario, what's happening, at least what we have observed with the experience from many customers, is quite often that results into a memory bottleneck. Right. So you have a finite amount of a memory from a GPU point of view. Maybe it's 32 GB or 40 GB, depends on the size of host you might be running with. But primarily, you are limited by that memory, what you have in a single GPU. And you see our out of memory errors, and you also see a lot of issues. So while what's happened behind the scene is quite often we have a customer saying that, okay, we are spending a lot of time in training, and then training becomes slow. And if it is become slow, that means it's not productive enough for our data scientists. And not only productivity, but it's also prevent them iterating from a multiple model development activity. So there are solutions out there, and we will touch upon those, what we call the distributed training solutions. And for that, I would like to hand it off to my colleague, Mani here. Mani, if you can take it over and talk about the distributed training solutions.
Mm-hmm. So thank you, Ritesh, for sharing how training works behind the scenes with SageMaker. So when we launch a training job, what SageMaker does behind the scenes, and touch basing on the challenges with the distributed training solutions. So there are two types of distributed training. One is data parallelism. The second one is model parallelism. Now, what does that really mean? I will have, let's say my business case is that I have this massive model that I want to train. And in order to train that massive model, I might have large amount of data, right? So how do I distribute my data across multiple nodes? And also, if my model is unable to fit in a single GPU memory, how do I split my model or divide my model, also known as sharding, across multiple nodes? So these are the two problems. And sometimes you would say that, oh, my model fits well in the memory, but I still keep getting out of memory errors. That may be because you have large amount of data, and with the model, it's okay, the model size is fine, but the data is so big that you either have to choose a small batch size, which might not be a good idea, because with the batch size, really defines your GPU utilization as well as the training efficiency. So we cannot reduce the batch size to, let's say, 1 in order to start with the training, and let's say our model will converge and we'll be able to get good results. Now, in order to avoid that problem, that's where we can divide our data into multiple nodes. So in case of data parallelism, we are only splitting our data set. And each of the nodes will have a replica of the model. So we are not doing anything with the model. All the nodes will have the same model, but the data set is split. And then the model will perform a forward and a backward pass, and then there will be a function to basically synchronize all the gradients that it has calculated. So that's what it is about, data parallelism. Now, let's say even our model was huge, and then and it cannot fit into a single node. Then we have to come up with a mechanism where we have to divide our model into multiple nodes. And trust me, I've tried it on my own. It's not that simple, because you have to know each of the parameters of the models. You have to know the model architecture very well in order to do that. And even when you do that, these deep learning models are sequential in nature, meaning you have a data, it will go through a forward pass, and then it will go through a backward pass, right? So how do we make sure that model parallelism is actually happening in that scenario? That's where the concept of pipeline comes in. So there is a concept called pipeline execution, which we'll touch base on. So that concept comes in, which really brings in the parallelism and model parallelism. So with SageMaker offers these two libraries for both data parallel as well as model parallel. So let's dive deep into these libraries and see how they can make our work easier.
Can I pause you here, Mani? Maybe a
Mhm.
question I have while you were talking about multiple CPU and GPUs. As a data scientist, when should I choose um, single node multi GPU versus multi node multi GPU?
Okay, that's a good question. So, and that's a common question. So what happens is, and just to repeat your question. So the question is, when we are training our model, when to select, like even my single instance can have multiple GPUs. And I can also have multiple instances with multiple GPUs. So for example, my one instance has 8 GPUs, and then when to add another instance or another those set of 8 GPUs, making it a total of 16 GPUs. So first of all, it will depend on the size of your model, and there is actually a quick calculation that you can do based on your model size. So what happens, and there is also a link in the documentation that I'll share with you that you can see how to basically quickly figure out the size of your model. So, and just to give you a small example, in general, if you are using a big model, it's like you can have one parameter usually takes like 20 bytes. So if you have like, let's say 10 billion parameters, then your model will be consuming 200 GB of memory. And you can take a look on the breakdown that we have on our link, and I'll share that link with you. So what happens is, in that scenario, then you have to figure out, okay, what is my memory for the single GPU and how do I divide? You also have to take into consideration the amount of data, the batch size that can fit into the memory. So based on these things, you can actually figure out when to use single instance and the multiple instance based on your memory. And one pro tip over here is, if you know that your model is so big, so you can also increase the size of your instance. So in that case, especially when we are talking about distributed training, there is also communication overhead, because when we are training the model, we are passing the gradients, and there is a lot of communication that is happening between the nodes. So if there is a single node, the communication is the time that it takes for the communication and passing through the gradients is also small. But if you add another instance, although we are adding another 8 set of GPUs, that communication time might increase. So have those considerations in your mind while deciding, so that will give you a good idea when to use what.
Got it. No, thank you very much.
Okay. So let's start with data parallel. So when we are talking about data parallel, think about, I have this huge amount of data and my model is good enough. It can fit into the memory and it still leaves some memory in my data for the batch size. So then what happens with the data parallel, as I mentioned earlier, is each model replica is there in each of these GPUs. Whereas when your data comes in, you divide the data and distribute it into multiple GPUs. So what we are doing over here is the model replica is there on each of these GPUs, but we distribute the data, the training happens, and we collect all the weights and the gradients that are calculated and then save them. So that's how we are working when we are talking about data parallel. Now, when we talk about model parallel, again, massive model now cannot fit into a single GPU memory. So with that, think of the things that we have to do. We have to first, as I mentioned earlier, understand model architecture, divide the model into subgraphs, place those models into the model partitions into different nodes. So all this requires a lot of time, and if you haven't done it efficiently, then your GPU utilization as well as the training will not be that efficient. So SageMaker model parallelism library, it helps you in automating this model partitioning. There is an option. You can choose to do the manual partitioning if you would like, but it provides you with the automated model partitioning. And I personally like to use that because it does the job for me. And When we have divided the model into different partitions, again, these deep learning models are sequential in nature. So we have to think of a mechanism where how do we do these executions? And that's where the concept of pipeline execution will come in, which I'll dive deeper. And since we're using SageMaker, it's a fully managed training. You don't have to manage the underlying infrastructure. Ritesh has already talked about it, so I'm not going to repeat those. So let's see what happens, what SageMaker model parallelism is doing for us. So the first is when we start with model parallelism, it will first, and it is an automated model partitioning if we have selected that. It will first analyze your model graph structure. It will then determine the weights, the parameters, and how these tensors will be exchanged. And after analyzing that, it will run a partitioning algorithm, which will actually divide the model in such a way that it will balance the activations, the parameters, and the weights, and also minimize the communication. And then place those partitions on devices to be executed in a pipeline manner. Now I've touched base upon pipelining. So let's see what pipelining is. So what happens is, when we are talking about pipelining, what it really means is that I have placed the model, as you can see on this slide, on the figure, right? So our model is basically divided into different GPUs. So when you say L1, L2, L4, think of them as layers of the same model. So what it's indicating that layer 1 is on one GPU, 2 is on the another, and so on. And now my data is coming in. So I provide a batch of a data. It will divide it into micro batches. Now, what is a micro batch? It's basically a subset of this mini batch or a batch, right? That it will create. It will pass that micro batch sequentially, and then it will calculate the forward. It will do the forward pass, right? So in deep learning, what happens is the intermediate layer outputs, they are called activations. And they're calculated during the forward pass. And then during the backward pass, these activations are used to calculate the gradients. So when you are feeding these micro batches sequentially, we also want to make sure that the GPU utilization is higher. So that's the job of pipeline execution. What it will do is, it will figure out how these micro batches will be executed. So there are two types of pipeline execution. One is simple, the other one is interleaved. With simple, it will first calculate all these micro batches will come in, it will calculate the forward pass, and then after all the forward passes are done for all the micro batches, then it will start with the backward pass. So you have to store the activations that are calculated by the forward pass. Now, that might not be very efficient because first you have to store all these activations. Secondly, let's say all the GPUs are done with the calculation of the forward pass, but GPU 4 was still working it. Then all these other 3 GPUs are actually waiting for it to finish before they can start with the backward pass. So that's where the concept of interleave pipeline comes into play, where it prioritizes backward pass. So for example, my batch comes in, my GPU calculates the forward pass, and then that part is done. And other GPUs are also working on calculating some forward pass, but they will not wait, because if the forward pass is done, we are prioritizing the backward pass for the same micro batch. So it will start with the backward pass. So that's how it's going to increase the GPU utilization. So interleave pipeline is, in most cases, you will find it better because it will minimize your idle time on the GPUs for the reasons that I just explained. So that's what we have for our interleave pipeline. So we have talked about what, so far what we have done is we have talked about how the features provided, some of the features provided by SageMaker. Then we talked about how training really works, because that's the focus of our today's workshop. Then we touched base on the concept of distributed training, and then we talked about how some of the features that SageMaker offers for data parallel as well as for model parallel. And the important point to note over here is, all of this is done behind the scenes for you, and you have with minimum lines of code for doing the model parallel. And that's what we are going to figure out in our lab today. Okay, in order to get started with the lab, we are going to provide you with event engine accounts, meaning we are going to provide you with the workshop accounts, test accounts. So you don't have to do the lab in your own account, because we are doing training a big model, and we'll be using a GPU, which might incur cost. So we'll be providing the accounts to you. And for that, what we are going to do is we provide your event hash, and you can follow along with me. So you have to first click on this link that we have provided you, which is dashboard-event-engine.run/login. So click on that link. You can copy the link and then open the browser. I'm using Chrome. Feel free to use that and paste it. And let me give you the event hash that you can use. So we have the event hash in the chat that you can use. And you will paste that event hash. That might be different for you, and it's different for me, so don't worry about that. Paste that event hash and click on accept terms and login. And make sure before you do that, that you are logged out of your AWS account. Otherwise, it won't work. It will give you an error. So accept the terms and conditions. And then there are options. So you can either choose to use email one-time OTP password or log in with your Amazon.com retail account. We don't charge you for anything. It's just for make security purposes. So I would go with email one-time password. And then I'll type my email and then do send passcode. And now I have to check my email. Give me 1 second so that I can check my email and get the passcode. Okay, so I have fetched my passcode, and then I'm going to paste that passcode and then sign in. Okay, so now we can see that we can log into AWS Console from here. So we'll click on that and then open console. And yay, finally, we are in AWS Console. And let's search for Amazon SageMaker. You can search on that, type SageMaker on that search box, and then click on Amazon SageMaker. Then on the left navigation, click on the studio, then launch SageMaker Studio. And for the workshop today, what we have done is basically, we are already providing you with the account. So this studio domain will be open for you, and you will see this user already created for you. So if you are new to SageMaker and you are logging in for the first time, you will not be that. You would have to create the domain. And we'll share the link for the first-time users who don't have a SageMaker domain. They can follow those steps and create a domain. There's just few steps that you have to follow, and you can create a domain. Once you create a domain, then you can add a user. So for the workshop, for the purpose of the workshop, this user is already added. So let's say, and click over here, launch app, and then click on Studio. So when Studio is launching, it takes like a few minutes. if it's launching for the first time, or it might be faster. Now we are here, so you will see this launch page. There are a lot of things that you can do on the studio, like use the jump start or build, automatically you can build the model. So there's SageMaker Autopilot. There is Data Wrangler, which is a visual interface using which you can, process your data. And so there are a lot of other features that SageMaker offers. And then once the features are processed, you can store it in the feature group. And as Ritesh mentioned earlier, we also have built-in MLOps capabilities. So you will see features like model registry, projects, SageMaker pipelines, and all those around that. But today we are focusing on model training. So let me give you the link for the repo. And let's start using our repository. Okay. So we have this GitHub repository, which is SageMaker examples that we are going to use today. So use the link that I've provided in the chat, and then you have to click over here, this branched icon, and then clone a repository, paste the repository link, which is the SageMaker examples GitHub repository, and clone. And then you can click on the left navigation. You will see this folder icon. You can click on that. And then you will see that this is happening, Amazon SageMaker examples. And on the bottom at the taskbar, you can see the repository is cloning in. So it will take like about a minute to clone the repository because there's so many examples in this repository, not just for training, but for all the different types of features, as well as some of the common machine learning use cases. So let's give it a minute, let it clone the whole repository, and then we can go inside this folder and see all the stuff that we'll be working on today.
Sorry. So while it's cloning, maybe Mani, can I ask a question here?
Yeah, sure.
Particularly, what example we want to try or going to run through today? Can you shed some light on that?
Yes. So what we're going to do today is we will, since we are focusing on the training, so we'll do that, but we'll primarily focus on model parallel training. And then for that, we'll be using our GPT-2 model, which is really big model with 1.5 billion parameters. And you can actually take these concepts that we are going to talk and train your own model as well. So I have personally trained, worked on the GPT-2 as well as a vision transformer model. So using the same steps, so literally using the same concepts. I've done that, and it's amazing. And that's what we are going to do today.
So I've heard many GPT type, right? Like one is GPT small, the one you talked about GPT-2, there is also a GPT-3, there is GPT-J. Where does it stop and what is the difference? I mean, 2 versus 3, it's a huge, right? GPT-2 is what, 1.5 billion, and I heard GPT-3 is even way bigger. So can you share some more?
Yeah, absolutely. So GPT-2, so mostly the difference is between the number of parameters, right? So if I have a project, let's say I'm to build a chatbot, right? Now, which model to use? So I would have to see how much amount of data that I have. So if I'm selecting a really big model, then I also have to make sure that I train it on, although these are pre-trained models, but if I have to, do transfer learning and train it on my own data set, I have to make sure that I train it on a big amount of data as well. And also it depends upon the resources. Like, do my problem really needs a GPT-3 175 plus billion parameter model? If yes, then by all means, definitely use it. And you can train 175 plus billion parameter on SageMaker. There's actually a blog written for training that 175 plus billion parameter, and that you can use, and I can share the link that you can refer actually. So it depends on your problem as well. So mostly the difference is between the number of parameters. And today in our example, we are actually going to train a GPT small model, which I think is close to around 300 million parameters. Not that big, but it's still big enough because we also want to make sure that we are able to finish it on time. So in the SageMaker examples, you can go inside the SageMaker example, scroll down, and go to training. So you would see this training folder. So double click on that, then double click on distributed training, then PyTorch, because we'll be using PyTorch, then model parallel. And you can see there are examples. We have GPT-J as well, GPT-2 and BERT, but we'll be using GPT-2. And then we'll start with this notebook. And we'll also go through the training script. So let me close this and start with training GPT-2 model. So let's look at what does this really mean. So just to give you a quick overview of what the GPT-2 model is. It's a transformer-based model, and it was first proposed by OpenAI, and their paper language models are unsupervised multitask learners. So you can, I really like to look at the papers, if not deeply, but at a high level, but that's just me because it gives me good knowledge about the model architecture, what the model is trying to do. So that way I gain like some knowledge and get some sense of what the model is about. And most importantly, how how they have trained the model and what parameters were used when they trained those models. So that gives a good idea. It's not required, but it's just gives you good background about the model. And in this particular notebook, we have Hugging Face, a library which has GPT-2 implementation. So we are going to use Hugging Face Transformer Library. And for those of you who are not aware of the Hugging Face Transformer Library, Hugging Face is a company which basically have a lot of pre-trained transformer models. GPT-2 is one of them, but there are so many. I think now there are about 15K plus models that you can, pre-trained models that you can use. I actually used one for the protein classification in my blog for doing protein classification. And that was a prod BERT model. So Hugging Face is really helping with that. So we'll be using Hugging Face Transformers GPT-2 implementation. Now, this notebook depends on a lot of files, but we'll focus primarily on the notebook. And let me give you a quick overview. So this train GPT simple Python file is an entry point to the script. So what it does is it will load the model. We'll provide we'll also import the SageMaker model distributed library. We'll wrap the model in the distributed model API that it provides, and we'll follow a lot of steps. So this training script has all those steps for enabling the distributed training. And then there is also data pipeline Python file, which basically has the functions preparing the training data, like the training data loaders and all that stuff. And then data prep. So this file will basically download and process your open prep text data set. It's a huge data set. I tried, and it was taking me about 3 to 4 hours just for data preparation. So we'll not use this in this workshop, but it's available for you. You can use this script to download and pre-process the data. But mind you, it will take 3 to 4 hours for you to do that. So, and there are steps in this notebook on how you can use this script. So that comes in handy. There's some additional resources and links that you can use for model parallel distributed training. It provides you with a lot of insights. I personally have reviewed this particular guide, like the whole information, couple of times because it has such useful tips, as well as it also explains a lot of concepts. So my suggestion, definitely check this out. This link is important. So with that, let's get started with some of the prerequisites. So when we are starting with what we need is, first we need the data. and we need to have our data in Amazon S3. As Ritesh mentioned earlier, you can have the data in a file system or like FSX or Elastic File System or S3. In this workshop, we'll be using S3, but this notebook does have some steps for FSX if you want to use it, but we will not use it in our lab today, but it does provide you with that code. So first of all, we'll basically install certain packages. Basically, we are upgrading SageMaker and installing SageMaker experiments. If you're using pip install like this, the way I'm using it, you can, when you run this cell, it will install these packages, and you have to restart the kernel. So that's the key. Otherwise, it won't get reflected. And also, one thing that I forgot to mention over here is for this particular notebook, although the training will happen on a GPU, but for the notebook, it might ask you to select a kernel and an instance. So we'll select this Python 1.10, PyTorch 1.10, Python 3.8 CPU. Now, why we need a CPU when we are training on GPU? Because we are not using the notebook compute to train our model. When we will launch the training job, then it will launch the GPU for me. The similar concept that Ritesh actually explained how it works. So that's how we are decoupling the compute. And that's how you're only paying for the amount of time the training was happening. So you're not paying throughout when I was writing code, and when I'm going through this with you, I'm not paying for the GPU. I'm only paying for this small instance, which has 2 virtual CPUs and 4 GB of memory, right? So one pro tip on optimizing on the cost. So let's run this cell. And for those of you who are new to this notebook kind of an environment, you can either click on this play button and run this cell, or you can use a keyboard shortcut. If you're on the Mac, I think it's Shift Enter, or just feel free to use this play button. And then you can do enable scrolling for outputs, so that you don't have to see everything on one screen, and you can just scroll it like this. It's just a pro tip over here. Small things, sometimes they matter, right? And with that said, you have to restart your kernel. Let's do that. Now our packages are installed. We have restarted the kernel, and now we'll move further to setup, do some setup, import some libraries, initialize the SageMaker client and the SageMaker session, get a default bucket. If you have your data on your own bucket, you can actually replace it. So let's run this. And this particular prepare your data set, we are not going to do that, but you can do it, and it gives you the steps on how you can modify and run it, because it does take 3 to 4 hours. And then we provide, because our data is on S3, so we have to provide the S3 bucket path. So in this example, we are using a smaller version of our data. So we'll be using those sample files and not training on the full data set because we haven't downloaded it, right? So when we run this cell, this basically downloads the data for us and uploads that data to a S3 location. In this case, since I haven't provided any S3 location, I'm just using the SageMaker default location and the prefix that we have defined earlier. Now, after the training is done, we have to store the model artifact. So we'll just provide an S3 output location, which we will use later. Now I have my data on S3. I also need to specify my training and the test channels. So that's how we use it. So since we are not using, you will see the mention of use FSX in between. We are not using it, so we won't go through it. But if you are using it, you have to change those flags. You have to provide a certain configuration that you will see as we move down to use FSX if you want to use it. So the primary difference between FSX and S3 is when you provide an S3 path, when it will launch the training instance, it will copy the data on S3 to your instance. especially when you have selected fully replicated. There are other modes as well, right? And if your data is on a file system like FSX, then when you launch the training instance, what it does is it basically mounts that file system to that instance. So it doesn't have to copy it. So you save time, and that's why it's faster. So just a quick explanation on that.
So a question on that, Mani. In what scenario, from your point of view, we should use S3 versus FSX?
Again, S3, I would recommend S3 for when you have large amount of data, because S3 is cheaper to use. FSX does give you some cost.
Right.
But if you are working on high performance computing and you really want to minimize on that time, you can use FSX. The reason I'm suggesting S3 is because when we are training our large models, and if time is not a constant over there, because anyways, training that huge model will take some time.
Right.
Right. So it's not that the training will happen like very quickly. So that way you can use S3. And with S3 also, you can use a different distribution type. If you're using fully replicated, it's only then when it will copy all the data before starting the job. But there are also other distribution types that you can refer, and I'll share the documentation with you. I don't remember on top of my head right now, which you can use, and they work really well.
Like the fast file mode and things like that?
Yes.
Okay.
The fast file. That's what I was missing on. Thank you so much, Ritesh, for providing that. It's a fast file mode. I have tested it myself. So I basically created a small experiment just to figure out what's the difference. So I was using FSX, I was using fast file mode. And to be honest, of course, FSX was faster, but fast file mode was also solving my purpose. So again, depends on the requirements, depends on the time that you have in hand.
All right.
Okay, so let's define our training and test channels. Now, again, this is an optional step if you want to use FSX, so you can provide those settings. You have to provide your file system ID. So that means that FSX file system is already there and the data is already there. When you create FSX, you will get this ID. You will also have to provide the security group of your FSX and the subnet, your mount path name, basically, that's the path where it will mount to. And the file system type that you have to mention, which we have already mentioned, and then use the SageMaker file system input function to provide those parameters. RW means read write, and then have those channels. So we are not going to run this because we are not using FSX. Now, the most important part, and I know Ritesh, you will have a lot of questions around that, because to be honest, when I first saw this, even I had so many questions in my head, like what's going on. So the next part is really talking about hyperparameters. And that's my favorite topic. So what happens with the hyperparameters is we can divide the hyperparameters into different sets. Let's take one set which talks about the model parameters. Like what are the hyperparameters for the model itself, right? Like learning rate, decay, warm-up, so on and so forth. So they are really dependent on your model. So right now we are providing some of these hyperparameters over here. Now the second set of models will be SageMaker specific, like SMP configuration. When I say SMP, it's SageMaker model parallel. So those might be related to the SageMaker model parallel configuration. And there are a couple of them over here. So we should go through some of these ideas on what parameters are. Right, Ritesh? Which one would you like to go first?
Yeah, I would really like to understand your optimization strategy, so your activation strategy, right? How you do the memory optimization, and let's start with that.
Okay, and before we start with that, because in order to explain how we save the memory, let's also do a brief overview of, because there is another thing that will come up, which is, sorry, I'm just scrolling up, which when we'll talk about the model configuration, which is our tensor parallel degree and the pipeline parallel degree. So what if we start with explaining those ideas and then move into the memory saving requirements?
Yeah, sure. Let's start with that.
Okay. So let's see what is pipeline parallel degree and tensor parallel degree and why we are even using it, right? So let's talk about that. So in order to do that, I'll switch a little bit of gears and I will switch to image to explain that. So what happens is when we have our big model, as I explained earlier, we divide the model into different GPUs. In this particular example, it's just showing 3, but usually it's a multiple of 2. So with that, so you have a model. My model has 5 layers. So it will divide the different layers of my model onto different GPUs, right? That's what we call as pipeline parallel. I think that was the word. Degree, right? So how I want to divide, like how many partitions of my model I want to do, right? So that's what it means. And sometimes there might be a scenario, right? That one layer by itself is so big that it doesn't fit into a single GPU memory, right? So when we are talking about the layers, we are basically saying tensors, right? So that might be that big, huge layer like this.
I see.
So then we have to divide the whole one layer into multiple GPUs. That's what the tensor parallel means.
I see.
That how do you shard the layer itself so that it can fit into a GPU memory? So that really depends on the model, like, and especially if you're doing training GPT-3, which is 175 billion parameters, you might encounter a situation like this. So you can use the tensor parallel feature of SageMaker. Now, to your previous question, right? What are the memory saving techniques?
Yep.
Yeah. So now they become even more critical, right? Because when we are training these large, like really big models, right? What we are doing is we have to optimize on the memory. So how do we optimize on the memory? So there are certain features which are provided by SageMaker, we call as memory saving techniques. So with the memory saving techniques, and let's get back to our notebook where we can see some of these memory saving techniques. So there are basically 3. One is the shard optimizer, that we can optimize on how do we use this technique for saving the memory. So optimizer state sharding, what it does is it will shard the optimizer state. So what is an optimizer state? It is basically a set of weights that describes the state of my optimizer, right? And then what it will do is when you enable that is that it will shard that optimizer state, meaning it will, the set of weights that we have, which are describing my state, it will shard it and spread it across the data parallel device groups. Now you would say we are talking about model parallel, where does this data parallel comes into play, right? So with the model parallel, you can enable DDP true. So there is a data parallel as well, because we are dividing the model, but we are also using a strategy to divide our data as well, because all the data cannot go through the model at once, right? We have to divide. And remember, we touch base upon the micro batches and everything. So that's what it is going to do. So you can use the optimizer state sharding whenever you are using a stateful optimizer, such as Adam or FP16 optimizer, which will basically store both the FP, the floating point 16 and the floating point 32 copies of the parameters. So that's what the shard optimizer is. Now, activation checkpointing. So let's first understand what are activations, right?
Right.
Now, in our deep learning, the way we have a deep learning model, we have different layers, right? So the output of the intermediate layers are called activations. And these need to be stored during the forward pass. So when I'm doing a forward pass through my model, we have these activations and we have to store those activations. Why? Because during the backward pass, we'll use these activations for gradient computation. So that's where we have to store it. Now, if you have a large model and you are storing all of these activations simultaneously in memory, right, that can create significant memory bottlenecks. So with activation checkpointing, or also known as gradient checkpointing, what it will do is, by using that, it will clear the activations of certain layers and then recompute them during a backward pass. So it's basically effectively adding this, we are trading, right? So we are effectively trading the extra computation time for reduced memory usage. So that's what activation checkpointing is.
Got it.
Now,
still memory optimization technique at the end of the day, so that we can fit in our model within the available memory within GPU.
Yes, absolutely. And another thing is, another technique is called activation offloading, which is directly using the activation checkpointing. So in the offloading, what we are doing is, rather than doing this recalculation, we are offloading the checkpoints to a CPU memory during the forward pass, and we load them back into the GPU for the backward pass of that specific micro batch. So again, we're just trying to utilize the resources that we have, right? So it saves the GPU memory. And when you have a big model, let's say something like this, memory is super important, right?
Yes.
And also there is this blog that I would provide, that I would recommend people to basically go through is, let me train 1.75 billion parameters. And I was actually showing you the screenshot from there. And it does talk about those techniques. So I won't scroll it throughout, but those techniques are mentioned, which I just shared with you. And you can scroll down to the bottom, and it explains you about those particular techniques. So we'll share this link with you. So it's a really nice blog in explaining how you can basically train such a big model. So getting back to our notebook.
Yep.
So let's run this cell. We provided the configuration. Now, in this particular example, we are providing with options. You can either choose to use GPU 30 billion or GPU XL, GPU small, and as mentioned earlier, there are difference in the parameter size. By default, if you don't change the model config over here, it will use GPT small. And in this today's example, we are going to use GPT small because otherwise it will just take a lot of time. So let's go to the GPT small. And I've already explained what is pipeline parallel degree, what is tensor parallel degree. But just to do a quick recap on those concepts, remember, pipeline parallel degree describes into how many segments your model should be sharded, whereas the tensor parallel degree basically talks about if you have a model which even this one layer cannot fit into a memory, then how do we divide that, right? So, and also, quick pro tip over here is your tensor parallel degree. When you pick this number, it should not be. It should be smaller than the number of GPUs on your single instance. So, for example, if let's say I'm using 2 machines which has 4 GPUs each, so I cannot have my tensor parallel degree more than 4. So it's the number of GPUs on each instance. So your degree cannot be higher than that. So that's just a quick reminder that we have to make sure.
Yep.
So now let's run this cell. Now on the instance type, we have to make a small modification over here. You can either use the P3 instances or the P4 instances, which are basically NVIDIA A100s, or you can use the G4 instances. So we'll switch to G4DN 12 extra large.
12x, okay.
Yeah. So what does this has is basically it's a NVIDIA T4 GPU, and one machine for this has 4 GPUs,
Okay.
right?
So
And
the other one,
then,
P4, has an 8 GPU. This one has a 4 GPU.
yeah, the other one that it was showing earlier had 8 GPUs, but this one has 4. So we're just trying to, it's a workshop setting. We are trying to optimize, and also it's a quick tip. You might just need 4 GPUs, and if you look at the pricing for G4DN, they are cheaper than P4DN. So it really depends on how big your model is, and select based on that, and also check out the pricing for these instances to make sure that you are training your large models in a cost-effective way. And since it has 4 GPUs, we would have to update the processes per host to 4.
Yep.
So let's run that.
And we are only, for our workshop, we are only doing one instance, right? So I saw your instance count as a 1 there, just making sure it's 1. So we are not doing cross instance, but
yeah, we are not doing it, but definitely with this notebook and the code that we have, you can try out and use. You can change the instances to more than 1, and it will work. So again, these were just setting up the, providing the base job name, setting up the pipeline parallel degree and the tensor parallel degree hyperparameters to a variable. And now we are going to create a Hugging Face estimator. So as Ritesh, you already mentioned about an estimator, and you did a walkthrough of that. So it's really providing the configuration, right?
Yep.
So in this particular case, since we are getting our model from Hugging Face, we are using Hugging Face. And when we use Hugging Face like this, what it means is it will basically use the AWS provided Hugging Face container, which is really optimized, and it provides a lot of features as well. So, although SageMaker behind the scenes is all containerized, you don't have to be a pro on containers or to use it, right? So we'll be using this. So when we say Hugging Face and we call this class, what we are basically saying is we are going to use the Hugging Face container. And then we provide the instance type, which is MLG4DN 12 extra large with 4 GPUs. Volume size, we have added additional volume size to 500 GB. So when we say volume size 500, that means it's 500 GB. So make sure that your volume size is greater than the amount of data that you have, the size of data that you have. Then the instance count. In our workshop, we're using 1, but you can try out, use more than 1 as well, and it will work. And then there are certain distribution options, right? So and when we are doing, say, model parallel, what we are doing is we're using MPI. Now, MPI. What is MPI? I know most of you will be aware of it, but I'll just do a brief introduction. It's basically a message passing interface, a fundamental communication protocol that is used for programming parallel computer programs. So when we are building any parallel computer programs, we use MPI. And there is an open MPI implementation, which is basically mostly used as a building block for distributed training systems. So, and you can use, basically, if I have to do it myself, everything, then I can use that. And it's fairly simple to use when it's one instance, but if it's more than one instance or a machine, then it becomes really tricky. So when we say MPI over here, we are providing the configuration, and SageMaker is doing that heavy lifting for us. So SageMaker will do it for you, so you don't have to worry about that. Now, the SageMaker model parallel. Of course, we have to enable the model parallel in our configuration. So we have enabled that. We have also enabled DDP, which is the data parallel as well. So what happened? So again, we are saying model parallel as well as data parallel. We are enabling that. And then I've already explained some of these parameters that we are using for optimizing for training our model. And one quick thing, this optimize, I forgot to talk about this here. So there are 2 strategies. In optimize, you can either optimize for speed or you can optimize for memory. So when you are optimizing for speed, then you will have copy of additional copies of the gradients and the tensors, because what we are trying to do is we are trying to minimize the communication overhead in that scenario. But when we are optimizing for memory, at that time, it will not have any duplicate copies of the parameters and stuff. So we are basically, it might have more communication overhead relatively, right? So what we are doing is we are actually selecting a trade-off based on what we want to optimize for. And the memory saving techniques that I have shared with you will take into effect if you optimize for memory. So just a quick tip over here, and what does this optimize really means?
So it's going back to that shard optimizer and activation checkpointing, right?
Yes.
Okay.
Yes. Okay, and then there is other configuration that we need to provide. We'll provide our other hyperparameters for the model, as well as some configuration that we have provided. So we are actually using that. We have to provide the PyTorch version. In this one, we're using 1.10, transformer version, Python version, which is 3.8. And once my model is trained, then we are providing where my model artifacts will be stored. So remember, we created that S3 output location. So we are providing over here. So this tells the training job, like when you are finished, save my trained model on this S3 location. And then I can use the model artifacts from there to deploy my model. And we can also you can also enable the checkpoint and provide the S3 location where this checkpoints will be saved, meaning that let's say you are training the model and it's a big model and it's taking like 5 hours or 9 hours or even more, right? Then in the checkpointing, when you provide the S3, when you enable checkpoint and you provide the S3 location, it basically saves the model at regular intervals and the train model at regular intervals for you. So you can actually look at the location that you have provided, the S3 location, so the checkpoints will be stored over there.
So can I ask you a question on that checkpointing, Mani? So let's say I'm training for a long duration, like a full day or 8 or 9 hour. Can I resume my training using checkpointing?
Yes, absolutely. Because when we say checkpointing enabled, we are basically saving the whole model state into the S3 location. And yes, that's the whole idea, that we can resume the training from this particular checkpoint, because the entire model state, like all the weights and the gradients, everything is saved over here.
Cool.
So this is what our estimator will look like. So let's run this cell. Okay, maybe I forgot to run the previous cells. Yes, I did. So let's run this, or maybe some other cell that I would have missed running. Oh, sorry about that.
S3 output or?
I ran the S3 output one. Yeah, let's see. Let's try it again. Okay. Sorry about a lot of scrolling. Yeah, it was basically this checkpoint URI was not defined.
Okay.
Yeah, so now when I executed that cell, it worked. And now when we do SMP estimator.fit, that's where the training will start.
Okay.
So let's kick that off.
Yes.
Yes. So now it will do all of that Ritesh you explained, right? It will launch the instance. It will use this training script that we have provided. It will copy that training script. It will copy the data from S3. It will run the script and will do the work for us, right?
Yep.
So let's wait for it to
It's
run.
not doing locally on this 2 vCPU 4 GB. It's launching its own instance and then doing the work for us. Yep.
Yes, and we can actually, once these instances are launched, we can actually see what's happening in the CloudWatch logs, and we'll do that. So it's basically telling you over here, preparing the instances for training, right?
Yeah.
So it's really cool.
So, while it's training, probably it might take a minute or two to get things ready. I had a couple of doubts in my mind, and maybe you can help me clarify. And particularly, I had doubts around the hyperparameters, right? So in the initial cell, and again, we may have to scroll up a bit, but there are certain set of hyperparameter you selected there, right? I mean, as a data scientist, quite often, even in my past life, we had to run multiple experiments to find the best of breed from a hyperparameter point of view. How you identified those that, okay, this is the value I'm going to use, and it's going to give me a certain accuracy?
Yeah, so as you mentioned, there's a lot of experimentation that goes into it. One is you can get a sense of it when you read the model paper and you do some research on it, but really it all boils down to the experimentation. So with that, SageMaker provides you with automatic model feature. So rather than providing the hard-coded values for the hyperparameters, you can provide the range of hyperparameters. Now, when we provide the range, you would say, oh, there are so many permutations and combinations. So how do I, limit my hyperparameters, or how do I search for the best hyperparameters?
Right.
So with that, you can actually select the strategy. So when you are with AMT or the automatic model tuning, you can select two strategies, random search or Bayesian search. When we say random search, think of all of these hyperparameter combinations as a grid. And randomly, it will pick the different combinations. And then based on the number of training jobs that you have specified, after that, it will provide you with the best hyperparameters. It's faster, but might not be the most efficient one. With Bayesian, what it will do is it will start with random, then it will use that knowledge for picking up the subsequent hyperparameters. So that's how Bayesian will work. So it's more efficient because it is using that knowledge that it has, that it wasn't using in the random search.
I see.
Yeah, and another quick thing that we also should talk about is, before we jump into another thing, is I mentioned about this training script, right? And we can go through it. But what I really want to do with today is this script, because we are providing a lot of options, right? We are saying that if this is the model, use this. If that's the model, use this. So this script is doing a lot. So what I want to do in this workshop is to make it simple for our audience, is to provide, if they have their own training script, how would they modify to make it for model parallel, right? That's the key point of the workshop.
Right.
So let's take a look. If you have a script, how would you modify to use it for model parallel with minimum lines of code, right? So we do have a documentation, and I'll share the link, because that's the whole point. I want you to go with some links and the knowledge about it. So when we are training our model, let's say it's a basic script. We are not talking about model parallel. There are certain steps that I need to do. I have to load my model, then I have to load my data, then I have to create a data loader if I'm using PyTorch or even for TensorFlow. Then I will have a data loader, and then I will have my optimizer. I will load my optimizer as well. Then I will create a training function, which will basically go through the different batches in my training data loader. And then for each of this, batch of data that we have, we'll pass that data into the model and calculate the loss. So this train function will be there, where you will basically, and then just to make it separate, the data passing to the model and calculating the loss, we can have that train step, right? So this train function, this is how we typically write our code, right?
Yep.
So for SageMaker model parallel, make sure that so some people just write this particular code, the train step code, inside the train function. So what I would recommend is not to do that, and keep it separate, and then you can call this function inside your training function, because we have to decorate it with smp.step, which I will come back later and explain what it does. Right. So we are doing it in a modular way. So let's first understand. Now, if I have this script and I have to change it to model parallel, what do I need to do? First of all, I have to import the SageMaker model parallel library. Then I have to initialize the backend.
Right.
So now I'm initializing it with this smp.init function. Then definitely I'm setting the device to CUDA because I'm using GPU.
Yep.
Then I will load the data set as I mentioned earlier. But now, because we are distributing our data as well, so to split our data, so there are two options. Either you can use the split dataset function provided by PyTorch, or you can use the distributed sampler function provided by PyTorch. And you have to split this data set based on the data parallel rank. And then you can figure out this data parallel rank from the SMP DP size. So this gives you DP's data parallel size. So this gives you that rank, and based on that, you split the data set. And then you provide that data set to your data loader. Now, when you are providing this to the data loader, make sure that you set drop last equal to true. Why? Because we want to ensure that our batch size is always divisible by the number of micro batches. Right? So when we do drop last true, and if it's not, then it will just drop the last.
Correct.
And then we load the model as we do it. But then to use it for the distributed one, we have to wrap the model that we have loaded. We'll simply pick the model and wrap it in the distributed model API. And similarly for the optimizer, we'll wrap it into the distributed optimizer API. And then we'll call our train function and pass these models and these optimizers rather than using these ones. So then we go to the train function, and the train function will enumerate on the batches of data, and it will call this train step. So when we have to enumerate on the batch of data, make sure that you are moving your data to device. To device means that you're moving your data to the GPU, right? And then it will call the train step. We don't have to do that for the model because we have already wrapped our model into the distributed model API. So we only have to do it for the data. Now, when this step is called, we decorate this step with smp.step, and we call this. So what happens when it sees this particular decorator? Remember when we were talking about our presentation that with the model parallel, it will trace through your model, it will determine the number of tensors and the weight. So this is what it's going to do. It will analyze your whole model architecture. It will determine the stuff. Then it will run the partitioning algorithm, and then it will partition the model into different nodes. So that's what happens when the first time this is encountered. For the subsequent runs, it's already there. So that's why sometimes when we run the first time when it hits this smp.step, it might take a little more time, but for the subsequent steps, it's done because we already have the graph, it's already distributed, we are good. So that's it, and it will return. Now, but one key point over here is, remember we talk about our data divided into micro batches. So whatever we are calculating the loss and all, it's for a micro batch. So we get the loss for the micro batch when we call this step. So we have to average across these micro batches. So we have to use the reduce mean type of a function to do that. And that's it. And then optimizer.step to start with the backward propagation. Backward pass. So that's pretty much it. So all we have to do is, if I summarize it into the steps, load your model, decorate with the SM decorator, load it with the distributed model API, load your optimizer, distributed optimizer after you have initialized your backend, right? Then you have the data set, load the data set, split the data set based on the data parallel degree, put it in your training data loader. While you are doing that, make sure that drop last is true because we want to make sure that our batches are divided by the micro batches. And then call your training function in the training step. Make sure the train step is decorated with SMP step, and then the loss that you will get is for the micro batches. So you have to do reduce mean to average the loss across the micro batches. Yay! So that's how you will do. And this script, the script that we were using.
It's a very small thing. It's like 30 lines of a code. That's it.
Around 13 to 14 lines of code. And here's the thing. These are the same concepts that we are using in this particular script, but you will see there is a lot of, when I look at that, you will see there's a lot of lines of code. It's mostly because there's a lot happening other than just this, but it's using the same concept.
Right.
And let's see what's happening with our training job. I think it's done.
Wow.
Let me just scroll through it. Yes, we are getting the losses. Look at that.
Yeah.
Yeah. So it's successful. I just want to see the success. I'm a little paranoid. Yes.
And it uploaded your model as well. So yes.
Yes. And you can also see all these logs because all the GPU that it configured, it's literally, it will tear down all the resources. So you're only paying for the amount of time that this training was running, which was 338 seconds.
Wow. So my G4 DN 12x large, I only pay for like 5 minutes and 38 seconds. That's it.
Yes, because our data set was also small, right? But in the real scenario, when people will be solving their business case, their data might be bigger. But yeah, we don't have to use like such a big 8 GPU size instance, right? 4 GPUs are good enough, and there are 300 million parameters. They're effective, they're efficient, and it solves the purpose, right? And we can see all these logs in the CloudWatch logs. So you can actually go to your console.
Let's see some logs, some metrics, and then maybe if you can also show us the model artifact where it's stored.
Okay. So let's go to the, so model artifacts are basically stored on the same S3 location, but I would say let's go through the training job. So in the training, so basically what I'm doing is I'm on the console, and then I basically search for SageMaker, and now I'm at Amazon SageMaker. And in the training, I can look at my training jobs, and you would see that it has completed. The other ones are basically I tried before the workshop, so don't worry of those. I wanted to make sure everything is working seamlessly. Yeah, but let's look at the one that we just did it during our workshop. So you can see that there is a lot of metadata that you can see, although your instances and everything are tiered down. So you're only paying for this amount, but you can see a lot of metadata. You can see which training image was used, basically which container was used, additional volume size, your instance type, count of instance, lots and lots of metadata, like where my training data was there, where is my test data was there. So it provides you the S3 locations, checkpoint, where was it stored, and then the hyperparameters that we use. So there's lots and lots of information that you can go through, but let me just quickly go through the logs. So in the monitor section, you can go and click view logs. And then you click on the log stream, and then you can see the logs. Now there are a lot of logs, right? So one quick tip over here, do view as text. Look, it becomes more readable,
Suddenly,
right?
yeah, the format is changed.
Yeah, and if I have to, let me do this, sorry. Okay, it's not working. So I just wanted to share about this. Somehow in my screen, it's showing like this. So I can also filter my logs. Let's say I do batch. If there is a word, it will actually filter out my logs. So it can do that. So wherever there is a batch word, so I can see that. And if I want to see, so I can basically filter the events. So it can see, okay, which loss. So whatever the words are there, I can search. And also, if I just want to look at the last logs and I don't want to go through everything, I can load the last 1 minute log. It's been more than 1 minute, so I can load the last 30 minutes logs and see what happened. So I don't have to really go through all the logs. Let's say if I just want to start. So sometimes I do 1 minute and then I do load more so that I can see just the previous logs that were there rather than going through the whole log file. And yeah, so it's pretty nice. And you can actually see the different batches, the different losses, and the speed that it's taking, the samples per second. Yeah, so that's pretty much it.
Yeah, no, that's nice. Is there any way CloudWatch also supports metrics, like what was our GPU utilization or something like that?
Yes, good point. So when we come to SageMaker over here, you can actually see some of these instance metrics as well. I think it might not be visible over here because our job was really small, but then you can change certain settings like let's set some custom stuff. Let's set it to last 5 minutes to see, but it really depends on how long the job was
Right.
running, but you can actually see it.
Yeah, ours
There
was
is an
very
option.
small, maybe 5 minute or yeah, 5 minute and
Yeah,
30 second, right? So yes, yeah.
yeah, it does provide you with those logs somehow. It's not showing over here, but that's okay. But you can see the GPU utilization
Right.
if your job is running there. Yeah, so that was pretty much about our training. And even in the notebook, we have provided the steps for our viewers at home or people who are walking, doing running this notebook with us. There are information about accessing the training logs, and there is some information on how you can deploy the training model for inference, and how do we save the model for TensorFlow or the PyTorch. So these are a few things. Just go through them. They're very useful. And yeah, so that was pretty much it. And thank you so much for your time. And in the end, last but not the least, let's share some links with our viewers,
Yes,
right?
absolutely.
Okay, so these are some of the links to get started on SageMaker. So you can look at those documentation along with the links that we have provided you while we were doing the walkthrough. So feel free to check those out, and feel free to reach out to me and Ritesh anytime. We are there. You can reach out to us on LinkedIn as well. So, and thank you so much for your time, and looking forward to connecting with you again sometime soon.
Awesome.
Thank
Thank you.
you.